In this video, we're going to look at how to name ionic compounds with polyatomic ions in their structure. Of the different types of nomenclature that we're going to have to name, this is the one that gives people the most trouble, not because it's that difficult, but just naming the polyatomic ions is something that people have to just work at. So again, the thing to think about here as we're talking about this, we're looking at how to name or write the formula for when one metal bonds to several nonmetals. Most of these polyatomics have oxygen in them, and then there's one other nonmetal. That's why a lot of times you'll see the phrase oxyanions, because it's oxygen with something else. So to go through the process of naming these, and more specifically talking about naming of these polyatomic ions, because naming the metals, that's easy. The name of these polyatomics it's based upon the non-oxygen element. So we see something like phosphate or nitrate, which is in biology. The name is based upon the non-oxygen element. Phosphorus, nitrate. So from that, we can determine what the first element is. Then, if there's a prefix or a suffix, that's going to tell us how many oxygens are in the formula. Now, big difference here. This is not nitride, because "ide" means alone. This is nitrate. That means nitrogen with oxygen. So a big difference there. Right here, this is what gives people the most trouble, is remembering this simple piece. "Ide" means alone. "ate" means with oxygen. And we'll look at some other endings here in a little bit. So here's the thing that is the best way to go about this. The most difficult thing to know is this first one, the blank 8, whatever that non-oxygen element is. Whenever something has the ending 8, it is the most common form that element bonds to oxygen. Usually it's 3 or 4 oxygens, so usually it's an O3 or an O4. Here's the problem. It'd been nice if 8 meant specifically 3 oxygens, or meant specifically 4, because then it'd be easy, because everything follows this pattern. The problem is this very first one is difficult because it's the most common. Now, what determines the most common? Well, the first one found was the most common. So what the 8 is with nitrogen is different than what the 8 is with sulfur, because nitrogen bonds differently to oxygen than sulfur. Therefore, you're going to see different ones be more common or less common. So what's the hardest part? You've got to learn the 8s. Okay? There's no way around it. Now, I've got a chart that I'll show you, the ion chart here, that shows that we can look at. And see if I have that actually attached. Good, I do. So we'll open up the ion chart here. And this is the very first thing probably listed under the notes for section 1. So you'll definitely want to have it. But what you're going to see is down here at the bottom of this chart are polyatomic ions. And you're going to see that they are broken down into different charges and a whole bunch of things that we'll probably talk about in class at one point. Well, if you notice, everything has the ending 8. Well, these are the ones you've got to learn, because if you know the 8, then everything else does fall into the pattern. So again, if you know the 8, then everything else falls in. So if we know that 8, if then we see something that has the ending ite, ITE, then that means there's one less oxygen than what the 8 has. If you see something has per blank 8, then that means there's one more oxygen than what that 8 has. And then if you see hypo blank ite, then that means there's 2 less oxygens than the 8. So again, what does this all fall back to? It all falls back to the first one. You've got to learn the 8s. Okay, I cannot say this enough. You've got to know these. If you know these, or if you know those, then the rest of them fall right into line. And the ion chart can help you. So, just give you an example here. Chlorate is ClO3 and has a -1 charge. That is the most common way that chlorine bonds with oxygen, O3. Well, if that's what we call chlorate, then chlorite is one less oxygen, O2. Okay? Again, ite, one less oxygen, per 8, one more, hypoite, two less. Falls in that pattern. Well, if chlorate is O3, then per chlorate is O4. And if perchlorate is O4 and chlorite is O2, because chlorate's O3, then hypochlorite is O1. Everything sits in this pattern. You know chlorate. Once you learn that one, the others are easy. Now, in the book, there's a chart. Well, they list all these extra ones. Makes the chart look bigger than it really is. You learn one, you're going to know the others. So let's look here at the next thing. I'm going to give you one. It's called sulfate, and it's SO4. So here's what I want you to do is write these down and have you pause. And just do this real quick. If sulfate is SO4 and it has a 2- charge, what are the others? 3. What would their formula be? You notice here, sulfur and oxygen's most common form is O4 with a 2- charge. Chlorine and oxygen's most common form is an O3 with a -1. It's different, but the ate and ite and hypo and per rules apply the same way. So what I'll have you do is pause this for a second. I want you to quick work on these, see what you get the answers, and we'll be right back. Okay, so you can see the answers to these other three. Sulfite. Ite means one less oxygen, so we see SO3. Still the same charge, 2-. Hypoite. 2 less oxygen, so SO4, SO2. Per sulfate. 1 more oxygen than sulfate, so we get SO5. Again, this right here, you've got to know what this page is showing you. You can figure this out, and you can do these, then the whole nomenclature thing is easy. It's a piece of cake if you can do this screen. All right, so let's look at some examples here. Well, if we start to bond these in a name and a formula setup, how is it any different than what we learned at the beginning of the section? It's not, because everything is going to be exactly the same. Let me do the first one here. Sodium chloride. If we said write the formula, well, sodium's a +1 charge. Chloride is chlorine. It's a -1. +1, -1, NaCl. Now, sodium chlorate. Sodium, it's 1 plus, chlorate. You've got to learn. Is ClO3, but the whole thing is a 1-. So how does sodium and chlorate bond together? Exactly the same as sodium and chlorine. Sodium has a +1 charge. Chlorate has a -1. So it takes one of each. So it's NaClO3. Now, if you really wanted to, you could put parentheses besides it, saying, okay, that whole thing has 1. You don't need the ones, but that's what it would be. Okay. Calcium sulfide. Calcium, 2 plus. Sulfide, sulfur, 2-. CaS. Calcium sulfate, Ca, 2 plus. Sulfate, SO4, and the whole thing is a 2-. +2, -2 cancel each other out. CaSO4. Calcium chloride. Calcium, 2 plus. Chloride is chlorine, 1-. CaCl2. Okay, cross charges. Calcium chlorate. Calcium, 2 plus. Chlorate, ClO3, whole thing is a 1 minus. Now, here's where you just got to be careful. We still cross charges, but the whole thing is a minus 1. So it takes 1 calcium to be canceled out by 2 chlorates. So when we cross charges, it's CaClO3 2. It takes 2 of these chlorates. Okay? It takes 2 of these, that whole thing, to cancel out 1 calcium. Don't say ClO6 or ClO3, don't put and not put a parentheses. You have to have the parentheses because this whole structure, it is in a calcium to chlorate ratio is 1 to 2. Okay? There's 2 of those ClO3s. Okay? All right. Now, here's what you got to focus on. You look at that ion chart. There's basically 16 eighths on that chart. Most of them are an O3 or an O4. Okay? The O3 eighths, all of them, but one are a minus 1 charge. Is there a nice, simple, easy way to learn these? Absolutely not. You just got to figure it out. Okay? Flashcards, looking at them, doing extra practice. You just got to know sulfate is SO4 2 minus. You just got to know chlorate is ClO3 minus 1, and work through it. Okay? There's no other way to say it. Okay, so naming these. Polyatomic. Everything's exactly the same that we did with ionic binary compounds. If you're given a formula, you need to write a name. Name the metal as is, and then name the polyatomic. Is it an 8, an ite, a hypo, or a per? So sodium sulfate, calcium chlorite, etc. Names to formulas. Well, you write down the symbols and the correct charges for each ion. The charges must cancel out. Everything's got to equal 0. Cross charges and be done. Last thing. Now, what about the elements that have the multiple charges? Well, again, just as a reminder, where you're going to do this here, you may see this occur. We've already talked about Roman numerals, okay? But there's an older naming system that may also occur. If you see the ending IC or OUS on a metal, for example, cupric or cuprous, it is telling you a specific thing about which type of copper. This is not very common, but it does occur in basically 3 chemicals that you'll see: copper, tin, iron, or 4 chemicals: copper, tin, iron, and chromium. If it's copper 2, which would be Roman numeral 2, sometimes you may see it written as cupric, okay, the Latin form of copper. If it's copper plus 1, which is Roman numeral 1, you may see the word cuprous. Now, IC and OUS doesn't refer to a specific charge, it refers to the higher one. So copper 2 is higher, it gets the ic. In tin and lead, or in tin 4 plus, it's higher, it gets the IC. The 2 plus, which is lower, gets the OUS. Okay? So nothing big deal here, but if you run across it, you can make those adjustments as needed. Okay? All right, last 2 things here. Acid nomenclature. The acid nomenclature will make sense once you've done the polyatomics, but really there's 2 types of acids. There's binary acids. Hydrogen bonded to something else. HCl, HBr, H2S. Real simple. Hydro, fill in the blank, ic, acid. HCl, hydrochloric, hydrobromic. Done. That's it. Now, oxyacids. So you have hydrogen, something else, and oxygen. Well, the name is based upon that polyatomic ion. There is no hydro listed. So now you're going to have H2SO4, HNO3, H2CO3. What you're looking for here is simply anything that has an 8 becomes an ic. Anything that's an ite becomes an OUS. And then we add the word acid. So if we see here, SO4, SO4 we know is sulfate. Sulfate in an acid, sulfuric. NO3, nitrate. Nitrate in an acid, nitric, and so on. Okay? So, if the acid has a polyatomic 8 in it, it becomes an ic acid. If it has a polyatomic ite in it, it becomes an OUS acid. So I have just different acids, and then in red are what the polyatomics names are, and then finally what the final acid name would be. So SO4 is sulfate, sulfate in an acid, sulfuric. SO3 in an acid, that's sulfite, sulfite in an acid, sulfurous, and so on down the line. So this rule applies for all acids, at least the ones we're worried about. Okay? So last little bit there about acids and what you're doing there. Okay? And we'll talk about those more as we get into later chapters. Okay, the last one, hydrates. Just a little thing here. Hydrates, chemicals that have waters sort of bonded to them. We're going to see this generic formula of a chemical formula followed by a dot and then X number of waters. This is very important because these waters are loosely bonded. They can be easily removed. So we're going to write them like this instead of this. Okay? Big difference. Those waters can be broken off fairly easily, but the other elements cannot be. So it's very important that we write them this way. How do we name these? Well, just name the first chemical. Copper sulfate, magnesium carbonate. And then name the prefix, okay, with hydrate. So I got copper sulfate, 5 waters, pentahydrate. Magnesium carbate, 2 waters. So magnesium carbonate, dihydrate. Okay? And that's basically all we're doing with the hydrates. We'll do this in a couple labs. Again, not a ton of information there. The book just glosses over it, but at least wanted to put it on paper for this. Okay? So this covers all the nomenclature, and again, at least get you started in the right direction, and obviously we can talk more about it in class.